last video of this chapter, we are on to something called linear approximation, also known as tangent line approximation. And it's something that is very closely tied in, obviously, to the idea of a tangent line. And what we are going to be talking about is how a tangent line relates to the curve itself. And so we know enough about tangent lines. We know that it intersects the curve, and we know that it shares the same slope, the same instantaneous slope that a curve has at a particular point. So the biggest idea that we're going to use here is that if you're right on the point, the tangent line has the same value. But if you're really, really close to the point, the tangent line will also have a very similar value. And so we've got this idea right here that linear or differentiable curves are called locally linear, which basically means, and we've seen this before with the whole differentiability stuff, if you zoom in really, really, really close to a curve, it'll basically straighten out and look linear. And once you get to a point where a graph looks linear, that's the slope of the tangent line. All right, so linearization, we are talking about just this whole idea of tangent lines and using tangent lines. So I wrote that this is a definition, but this is pretty much the definition right here. So if f is differentiable, notice that's usually a precursor to whatever we're going to use, then the equation of the tangent line is the linearization. And so linearization basically means to make linear. And so if you zoom really, really close in on a graph and then kind of match that linear piece to a tangent line, the tangent line itself is called the linearization. And so they're one and the same. They are synonyms of each other, tangent line or linearization. And so you could see the word linearization on the AP test, and it means the exact same thing as the tangent line. So I want you to make sure that you know that vocabulary word as well. Okay, so example 1, find the linearization, aka find the tangent line, and so we're going to have a little bit of practice with that, of this function at x equals 0. So we are going to start off with that. We're going to find the tangent line of this graph at this point. And so we'll get some tangent line practice because I know a couple of us have been struggling with tangent lines, mostly what to do with the slope. So let's start off with the derivative. I guess we can write down just our generic tangent line like this. Okay, so there's our generic tangent line. Here's the x value that's given to us. So for us, it's going to be 0. The y value you have to find. You have to find that by plugging in x equals 0 into the original function. And so when we plug in y1 is the function value at 0. Okay, so we plug in the function value 0, we get the square root of 1 plus 0, which of course is 1. And so that's this y value right here. And then the slope is the derivative defined at that particular point, at this point, x equals 0. So start with f prime. F prime of x is going to require a little bit of a chain rule. This, remember, is 1 plus x to the 1/2 power anytime you've got a square root. And so the first thing we do, the 1/2 power goes out front as a coefficient. Power drops down to a negative 1/2. And then because there is this nested function here, we multiply by our correction factor, which is the derivative of the nested function. So the derivative of 1 plus x, it's just a linear piece, and its derivative is 1. Okay, so we don't really need to do much to clean that up because we're not giving the derivative as an answer, we're giving the derivative at a point as our answer. So the next thing we want to find is the derivative at this particular x value that we looked for. That's the only point where we care about the derivative. We don't care about the function, we just want to know what the slope would be at this particular point, and so we plug in the 0. And then, of course, times 1, which that part I don't really need to write. 1 plus 0 is 1, and then 1 raised to the negative 1/2 power is still just 1. It would be 1 over 1. And then I multiply times 1/2. So my slope is 1/2. So we're going to put this all together into a tangent line. So y minus, my y value came out to be 1, equals, and then I plug in the slope, 1/2, and then x minus 0. So let's clean this up a little bit. Now this is something that's going to seem a little weird because we've gotten in the habit of leaving everything in point slope form, which is this point or this form right here. And so normally if all we're coming up with is the tangent line, we would leave it like this. But eventually we need to answer this question. Use it to approximate the square root of 1.02 without using a calculator. So we are going to actually turn it into slope-intercept form, which is kind of abnormal. We don't do it very much, but it's very, very quick algebra. All we do is we distribute this 1/2, and that would just be a 1/2 x, since this, of course, is 0, and then we would add the 1 to both sides. Okay, so we have y equals, this is a 1/2 x plus 1. So I just want to show you, just this one time, because I can't show you enough what these tangent lines actually mean. So I'm going to show you the original function, which is the square root of 1 plus x. So it's a nice curve. Notice it only starts here at -1 because I'm not allowed to plug negatives into a square root. And if I plugged in something less than -1, this would be negative. So in the next, I want to plug in the 1/2 x plus 1. So this is our tangent line at x equals 0. So you can see right here, it touches the line at 0, 1. They have that same intersection point. And then if we were to zoom in on this point, the tangent line and the original function would become practically indistinguishable. So I'm going to zoom in right at that intersection point. So here we are, we're a little bit closer. You can see that it lines up really nicely. Oops, we're zooming out. That's the wrong way. Zoom in. There we go. Okay, so zoom in on that center. There we go. That's what I wanted. So you can see right there, as we get closer and closer to this point, let's do it a couple more times. You can see that right around that point, right at the point, of course, they intersect. They're one and the same. But as we get farther away, let's zoom in just one more time. As we go away from that point, the closer we are to that one point of intersection, the more the tangent line looks just like the curve. Obviously, as we go away from the intersection point, the curve bends away and the tangent line stays straight. But the closer we are to that intersection point, the more the tangent line is going to mimic that actual curve. And we can get ourselves to a point if we zoom in so closely that they're indistinguishable from each other. So you can see that's very, very close to looking straight because we've zoomed in far enough. We have a width of 0.6 units approximately. If we look width and then a height of about 0.4 units. So I bet if we go in just once or twice more, they would be, there we go, twice more, and you can barely tell them apart except at the ends. All right, so that's what it means to be locally linear, is you can zoom in far enough to make your curve look linear. All right, so back here, we are going to write L of x equals 1/2 x. L stands for linear. This is the notation that we're going to use in this section when we are asked for the linearization. So our goal is to find this value right here. Okay, so our goal is to find f at, and we want the square root of 1.02, which means we want the square root of 1 plus 0.02. So we want to know what the function value is at 0.02. Well, most of us probably can't take the square root of 1.02 in our heads. We are going to assume that we would be doing this without a calculator. So our goal is to find this actual function value. What we're going to do, because 0.02, that's pretty darn close to 0, where this tangent line happens. And so we just showed by looking at that graph that if we're pretty darn close to that point of tangency, anything we approximate is going to be really close to what the actual curve is. So we are going to approximate this with the linearization at 0.02. Okay, so we're going to plug the 0.02 in here. So L of 0.02 is 1/2 times 0.02 plus 1. So half of 0.02 is 0.01 and then plus 1. So our approximation is about 1.01. So that's the first part of our answer. Next part of our answer is we want to check the accuracy. So I'm going to write down a percentage error formula. Squeeze this in here. So percent error, this is a formula that you guys will have to use in this section. We take the absolute value of the actual value minus the estimation and then over the actual value times 100%, because then you want to get a percentage. Okay, so we're going to plug that in. And now, of course, we do have our calculator. I just told you earlier that we're pretending as if we don't. And many of you may be wondering, why can't we just plug the square root of 1.02 into our calculators? Well, it's not really the point. It's more like we're figuring out how to use a tangent line to approximate something. And that will be very important on the AP test. So we plug in this formula right here. So we're going to set up a fraction. And then absolute value can be found right here on the Inspires, and there's an absolute value in the math menu on the TI 83s and 84s. So we're going to plug in the actual value, the actual square root of 1.02, minus our approximation of 1.01, and then over the actual value of 1.02, and then all of that times 100%. Okay, so we end up with 0.00, let's do 0.00490, 3 sig figs. Okay, so there was only this much error in our estimation, which means it was a pretty darn accurate estimation that we just made. Okay, so first example, we're just going to look at example 2 and 3, and then we're going to save the AP problem for when we're back together. Okay, so find the linearization. So again, that means tangent line. So first we want to find the y value. We want the y value at pi over 2. So we plug that in. Cosine of pi over 2. Well, that's the top of the unit circle where the cosine is 0. So that is our y value. So the point of tangency is pi over 2, 0. So that's a point on this original curve, and it's going to be the point where the tangent line intersects the curve. So we call it the point of tangency. Then we want to find our derivative. The derivative of cosine is negative sine. Keeping nice, easy derivatives here. And then the derivative at the point of tangency is the negative sine of pi over 2. The sine of pi over 2 is 1, so this is a negative 1. All right, so those are the points that we need to come up with our tangent line. So y minus the y value, which is 0, equals the slope, negative 1, and then times x minus the x value. Okay, so we can clean this up. Obviously, the 0 isn't going to do anything. I can distribute the negative 1, and my linearization will be a negative x plus pi over 2, because I distributed this negative 1. So there's my linearization. So find the linearization. Here it is. We want to use it to approximate the cosine of 1.75. Okay, so cosine of 1.75, I want to plug that in for x. So I am trying to approximate, I want to estimate the function value at 1.75 with the linearization at 1.75. Okay, so now this one's kind of obnoxious because of course it does say without using a calculator. Let's pretend that we had a calculator that can't do trig. I don't know. So linearization at 1.75, we are going to plug it right into this linearization function here. So negative 1.75 plus pi over 2. So again, we are going to pretend that our calculator just can't do trig. So negative 1.75 plus, and then there are pi buttons in all sorts of different places. Whoops, that is times, not plus. That's plus. Okay, so our approximation, now we want to keep as many decimal places as possible. So I'm going to write literally every single one that my calculator screen just gave me. Remember, we don't ever, ever, ever round until the end. I keep telling you guys 3 decimal places, but we don't do that until the very end of the problem. Our error formula would be all screwed up if I just gave you these 3 digits instead of all of them. Okay, so finally, percent error. And that is the same formula that I have up above right here. So in our calculator, we do absolute value of the actual value. So now I can plug in the actual cosine of 1.75 and then minus this value. I'm just going to paste it right in there. And then over the actual value of the cosine of 1.75 times 100%. Okay, so let's see. That should always be absolute value. I'm sorry. What did I? This should be around the entire thing. Let's try that again. I was wondering why that came out to be negative. So that should be around the entire thing. So my percent error would be 0.537. So here's where we go to 3 sig figs for our final answer. So 0.537% error. Okay, so quite a bit different. This one was significantly more accurate because the error was so low. So a lot of you guys from science understand the way that this percent error works, or percentage of error works. Probably in experiments that you're doing in science, you're like 10% error. So something that we're doing at the tangent line is going to be a very, very accurate value. Okay, one more. We flip the page. Okay, so use a linearization. So this one's a little bit unusual because example 1 and example 2, I gave you kind of so much direction as to what we wanted to use. So what we're going to do with this one is we have to come up with our own function. So the function we're going to use is the square root of x, because that makes sense. This is a square root function. And then we're going to try to figure out what value we know for the square root function that's pretty close to this one. So we don't know the square root of 123, but we do know the square root of 121. So the x value that we are going to use is 121 because that's one that we know, so that's going to help us find our point of tangency. So we want to find the linearization of this function at this point, and then we're going to use it to approximate this. So again, kind of more of a general question here where I didn't give you quite the specific information that I did with the other ones. So you got to kind of use your heads a little bit to see which one makes the most sense for this function, and 121 would be the closest perfect square. So the function value at 121. I just plug it into my square root function, and we know the square root of 121 is 11, so that's going to be the y value. So my point of tangency is 121, 11. So that's a point on my original function, f of x, and it is going to be the point where my tangent line intersects that original function. Okay, so then f prime. F prime is the derivative of this. 1/2 comes out front, power drops down to a negative 1/2. And since this is just a very neat, clean, no nested function sort of situation, I don't have to do the chain rule. But I do need to find the derivative at 121. So 1/2 times 121 to the negative 1/2. So 1/2 times 1 over 11, which is 1 over 22. So that's the slope that we're going to use. All right, so what that means is if I'm looking at my square root function, right around this point, every single time x goes up 1, the y value goes up just 1/22 of a unit. All right, so I'm going to use my tangent line. Y minus 11 equals the slope, and then times x minus the x value. Okay, I'm going to clean this up a little bit. Okay, so I am going to do 122. I'm actually not going to clean it up all that much. I think I'm actually just going to add the 11 over. Might as well. No point in dealing with ugly fractions when you can just leave it right like that. Okay, so we are going to use the linearization to approximate 123, the square root of 123. So I'd like to know the function value at 123, but I can approximate it with the linearization of 123. Okay, so 1 over 22, and then times 123 minus 121 plus 11. So like I said, right here, what this slope means, it means every time my x value goes up by 1, my y value goes up by 1 over 22. So my x value is going up by 2, which means that my y value goes up by 2 over 22, which is 1/11. So 11 and 1/11 would be my approximated value, or whatever that decimal turns out to be. I was going to say 0.1 repeating, but that's a lie. Okay, so percent error. We are going to plug in to our percent error formula. So absolute value on the outside, fraction on the inside, the actual square root of 123 minus our approximation, which is 11 and 1/11 over the actual square root of 123. And then we take all of that times 100%. All right, so this one is pretty darn accurate too. We've got 0.00 and then 336. So 3 sig figs. So pretty accurate for that one as well. Okay, and then like I said, this AP problem we are going to do all together.